Tiny galaxies are rewriting the rules of the cosmos. These dwarf galaxies, the smallest and most abundant star systems, are not just celestial footnotes. They are the unsung heroes of cosmology, holding secrets that force us to question the very foundations of our universe. By the end of this journey, you will see the night sky in a completely new light. We are about to explore 25 of their strangest discoveries, from ghostly galaxies made of almost pure dark matter to cosmic anomalies that appear to have none at all. How can something so small hold such immense power over our understanding of everything? That initial promise of countless tiny galaxies creates our first great cosmic puzzle. Our most powerful computer simulations, built upon our best understanding of dark matter and gravity, paint a very specific picture of our cosmic neighborhood. They show the Milky Way not as a solitary island, but as the heart of a vast archipelago. These simulations predict that thousands of dwarf galaxies should be orbiting our own, like a swarm of fireflies around a lantern. Yet when we point our telescopes outward, we see only a few dozen. This glaring mismatch between theory and observation is known as the missing satellite problem, and it is a problem that strikes at the very core of cosmology. Where did all those galaxies go? One compelling idea is that they are not missing at all, but are simply hiding in plain sight. Perhaps the vast majority of these predicted dwarfs formed so few stars that they are almost entirely dark, composed of nothing but the mysterious dark matter that the simulations rely on. They would be ghost galaxies, invisible to our current surveys, their presence only detectable through their subtle gravitational tugs. Another, more profound possibility is that our simulations are wrong because our understanding of dark matter itself is flawed. Maybe dark matter is not cold and slow-moving as we have long assumed, but is instead warm or even interacts with itself in ways we have not yet imagined. This would change how it clumps together, potentially forming far fewer small galaxies and solving the problem at its root. So we are left with a fundamental choice. Is the universe emptier than we thought, or are we simply blind to a hidden population of dark galaxies? This first mystery forces us to question whether the problem lies in the cosmos or in our own perception. This overwhelming emptiness points to a second, even more startling discovery. Dwarf galaxies are not just dominated by dark matter, they are almost entirely made of it. In some of these tiny systems, the ratio of dark matter to normal matter is an almost unbelievable 99:1. This makes them the most dark matter-dominated objects we have ever found in the entire universe. The evidence for this comes from watching how stars move within these galaxies. Astronomers measure the velocities of these stars, expecting them to orbit slowly in such a small, faint system. But the stars are moving incredibly fast, far too fast to be held in place by the gravitational pull of the visible stars and gas alone. It is like watching a handful of bees orbiting an invisible giant. Their frantic speed tells us that there is a tremendous amount of mass creating a powerful gravitational field, a mass we cannot see. This invisible mass is dark matter. The implications are profound. Because dwarf galaxies have such simple structures and are so overwhelmingly composed of this mysterious substance, they act as pristine, natural laboratories. They offer us a clean view of how dark matter behaves, free from the complex mess of gas, dust, and magnetic fields that complicate studies in larger galaxies. Take the Draco dwarf, a small satellite of the Milky Way. Its mass-to-light ratio is extraordinarily high, meaning for every bit of light its stars produce, there is a staggering amount of unseen mass holding it all together. Studying galaxies like Draco is like having a direct line to the secret architect of the cosmos, allowing us to probe the fundamental properties of the stuff that makes up most of the universe's matter. This incredible dark matter dominance points to an even deeper history written in starlight. many dwarf galaxies are not just massive for their size, they are also astonishingly ancient. They are cosmic retirement homes for some of the oldest stars we have ever observed, stellar relics that formed when the universe was in its chaotic infancy. To understand their age, astronomers act as cosmic chemists, using a technique called spectroscopy to break down the light from these distant suns. The story is told by what is missing. The first stars in the universe were forged from only the two simplest elements, hydrogen and helium, created in the Big Bang. They lived fast and died violently in colossal supernova explosions, and in their deaths they forged the first heavier elements, what astronomers call metals. These metals then seeded the next generation of stars, so a star with very low metallicity, one with almost no traces of elements like iron or carbon, must be a member of that first or second generation. It is a pristine fossil from a time before the universe was polluted with heavy elements, and it is within the quiet, simple dwarfs that we find these ancient stars in abundance, far more than in grand spiral galaxies like our Milky Way. This is profoundly strange. It suggests that these small, faint galaxies were among the very first structures to clump together and light up with stars, acting as the building blocks of the larger galaxies we see today. Yet while the universe evolved around them, with galaxies colliding and merging in a cosmic frenzy, these dwarfs have remained relatively unchanged for billions of years. They are not the building sites of today, but preserved archaeological digs. Their quiet, simple lives have allowed them to safeguard the oldest stellar populations, offering us a direct look into the conditions of the early universe. You are looking back in time not through a powerful lens, but by studying a star that has been shining since nearly the beginning of everything. But this ancient starlight reveals another layer to their quiet nature. While some dwarf galaxies hold the universe's oldest stars, many have produced almost no new ones since that initial burst. Astronomers call them feeble, a term that perfectly captures their profound and puzzling lack of activity. These ultra-faint dwarfs are cosmic deserts where star formation has been on hold for billions of years. This stands in stark contrast to larger, vibrant galaxies like our own Milky Way, which contain brilliant nebulae, vast clouds of gas and dust constantly collapsing to birth new stellar generations. So why are these small galaxies so barren? The answer lies in their gentle gravity. A dwarf galaxy possesses a shallow gravitational potential well. Think of this as a very wide, very shallow pond rather than a deep, steep-sided lake. It does not take much energy to disturb it. A single supernova explosion, the violent death of a massive star, can generate powerful shock waves. In a large galaxy, its deep gravity well can absorb this energy, but in a feeble dwarf, that same explosion can violently push all of the remaining gas and dust right out of the galaxy. It is like a firecracker going off in a shallow puddle. It blasts the water away, leaving the pond empty and unable to fill again. This process, known as quenching, effectively shuts down a galaxy's ability to make new stars. Another cosmic event may have sealed their fate early on, the epoch of reionization. When the first stars and galaxies lit up, their intense radiation flooded the universe, heating the diffuse hydrogen gas and making it too energetic to collapse. For a small galaxy with weak gravity, this external heat was a death sentence, preventing it from pulling in the fresh gas needed to continue its stellar production. So a feeble dwarf galaxy is not lazy. It is a victim of its own gentle nature, its star-forming potential easily snuffed out by both internal violence and the harsh conditions of the young cosmos. They are frozen in time, not by choice but by celestial circumstance. This quiet, ancient existence is not the destiny for every dwarf galaxy. Some meet a far more dramatic end, unraveling into spectacular rivers of starlight that flow across the cosmos. These are tidal stellar streams, the ghostly remnants of dwarf galaxies that ventured too close to a giant. When a small galaxy is caught by the immense gravitational pull of a massive spiral like our own Milky Way, it does not simply crash in. Instead, it is slowly, methodically torn apart over billions of years by tidal forces. The side of the dwarf galaxy closer to the Milky Way feels a much stronger gravitational tug than the far side. This difference in pull stretches the galaxy, pulling its stars away in long, graceful arcs that eventually encircle the predator. The most famous of these celestial rivers is the Sagittarius Stream, the dissolving corpse of the Sagittarius dwarf elliptical galaxy. It wraps around our entire galaxy like a great loop of cosmic tinsel, a visible scar from an ancient act of consumption. This process is galactic cannibalism, and it is how large galaxies have grown throughout cosmic history, feasting on smaller neighbors. But these streams are more than just fossils of destruction. They are incredibly sensitive tools for measuring the invisible. As a stream of stars orbits the galaxy, its shape is delicately molded by the distribution of dark matter in the Milky Way's halo. By mapping the precise path and subtle kinks in a stream like the Sagittarius Stream, astronomers can essentially weigh our galaxy's dark matter and chart its shape. It is like tracking a floating leaf on a pond to deduce the unseen currents beneath the surface. Every twist and turn in that river of stars tells a story about the gravitational landscape it is moving through, revealing the hidden architecture of our own galactic home. Just when we thought we understood the rules, the cosmos throws us a curveball. The idea that every galaxy is anchored by dark matter is so fundamental it feels like a law of nature. But then we found the outliers, galaxies like NGC 1052 DF2 and DF4. These are not the dark matter-dominated behemoths we have come to expect. Instead, they appear to be made of almost nothing but the stars we can see. The evidence for this comes from a careful celestial weighing of these systems. Astronomers measured the motions of compact star clusters orbiting within these galaxies. In a normal dwarf, these clusters would be whipping around, held in place by the powerful gravity of an unseen dark matter halo. But in DF2, the clusters were moving slowly, almost lazily. Their speeds were exactly what you would predict if the only gravity present was from the visible stars themselves. There was no need for any dark matter glue to hold the galaxy together. This is profoundly strange. It directly contradicts the standard model of galaxy formation, where dark matter acts as the essential scaffolding. Without its gravitational pull to gather gas in the early universe, normal matter should never have clumped together to form stars and galaxies in the first place. So how could a galaxy form without its fundamental ingredient? The discovery has sparked an intense debate. One possibility is that these galaxies are real anomalies, challenging our most basic assumptions. Perhaps they formed in a unique way, maybe through a violent gas ejection during a galactic collision that stripped away their dark matter, leaving behind a naked collection of stars. The other, more cautious possibility is that our measurements or interpretations are flawed. Maybe we are viewing these galaxies from an angle that masks their true dynamics, or perhaps there is something we do not understand about how to weigh them correctly. Either way, the existence of these seemingly impossible galaxies forces us to question one of our core beliefs. Are we seeing a crack in the foundation of cosmology, or simply a mirage in the data? The existence of galaxies seemingly devoid of dark matter is not the only cosmic paradox challenging our theories. Another ghost has appeared in the machine, a class of objects so strange they stretch the definition of a galaxy to its limit. These are the ultra-diffuse galaxies, cosmic phantoms that haunt the crowded realms of galaxy clusters. Imagine finding a balloon the size of a city bus, but one so thin, so ethereal, that it weighs barely more than the air around it. That is the scale of this mystery. An ultra-diffuse galaxy can be as wide as our own grand Milky Way, spanning tens of thousands of light years, yet it contains only a tiny fraction of the stars, perhaps just 1% of our galaxy's stellar population. Their light is so desperately faint that they blur into the background darkness of space, which is why they remained hidden for so long, even in our own cosmic backyard. They were first discovered in large numbers within the Coma Cluster, a dense metropolis of thousands of galaxies. This location makes their survival all the more baffling. A galaxy cluster is a violent environment filled with hot, turbulent gas and powerful gravitational tides. A structure as large and fragile as an ultra-diffuse galaxy should be like a spiderweb in a hurricane, instantly shredded and torn apart by these forces. The fact that they not only exist but are abundant in such a place is a profound puzzle. How do these cosmic ghosts endure? Astronomers are investigating two compelling and opposing theories. The first suggests these are failed galaxies. In this scenario, an ultra-diffuse galaxy formed with a normal amount of gas early in the universe, but for some reason, its star formation was incredibly inefficient. Its gas never condensed properly to birth a rich population of stars, leaving it a vast, empty expanse, a galactic skeleton that never gained flesh. Its diffuse nature might be the very reason it survives, as it offers little substance for the cluster's destructive forces to grab onto. The second, more radical idea is that these ghosts are not fragile at all. They might in fact be among the most massive galaxies in the universe, but their weight is hidden. This theory proposes that ultra-diffuse galaxies are encased in incredibly massive and incredibly spread out halos of dark matter. This immense but invisible gravitational anchor would hold the galaxy together against all the chaos of the cluster, like a ship with a deep, heavy keel that remains stable in the roughest seas. So we are left with a haunting question. Are we looking at the faintest, most failed galaxies or the most heavily armored titans disguised by their own ghostly light? This monumental power to reshape the cosmos stands in stark contrast to their feeble appearance. We now face a discovery that turns these tiny galaxies into cosmic revolutionaries. The collective light from countless dwarf galaxies in the early universe is now believed to be the primary force that ended the cosmic dark ages. This pivotal event is known as the epoch of reionization, and it was the moment the universe underwent a fundamental phase change, transforming from an opaque fog into the transparent expanse we see today. For hundreds of millions of years after the Big Bang, the universe was filled with a thick soup of neutral hydrogen gas. This gas absorbed the energetic ultraviolet light from the first stars and galaxies, trapping the cosmos in a pervasive gloom. Then something happened. A great cosmic dawn broke and the fog began to lift. The leading suspect for this monumental cleanup job is the humble dwarf galaxy. This seems paradoxical. How could these faint, unassuming systems, many of which we now see as feeble and inactive, generate enough radiation to strip electrons from hydrogen atoms across the entire universe? The answer lies in their sheer numbers and their unique nature in the ancient cosmos. In the early universe, dwarf galaxies were not the quiet retirement homes we see today. They were prolific star factories, and their massive, brilliant stars blazed with intense ultraviolet light. While a single dwarf galaxy's contribution was small, the combined output from billions upon billions of them, shining across the vastness of space, created an overwhelming background radiation field. It was a cosmic chorus of countless faint voices, whose collective song was powerful enough to ionize the hydrogen gas, splitting it into protons and free electrons and clearing the fog. Think of it like a vast field of dandelions. One dandelion releasing its seeds is a minor event, but a billion dandelions doing it at once can transform the entire landscape, seeding it for a new era. These dwarf galaxies did not just light up their own small corners of space. They fundamentally altered the nature of the universe itself, turning it into a medium through which light could travel almost freely for billions of years. This realization elevates them from celestial footnotes to the primary architects of the transparent cosmos we inhabit. Their faint, ancient light, which we struggle to see even with our most powerful telescopes, once flooded the entire universe, ending its long, dark night and setting the stage for everything that was to come. This structural chaos is a signature trait of the dwarf galaxy world. While their larger cousins, the majestic spirals and smooth ellipticals, follow a kind of cosmic etiquette, dwarf galaxies break all the rules of form. They present a wild menagerie of shapes, from perfect, ancient spheres to utterly chaotic, irregular blobs that look like splatters of stars against the dark canvas of space. This sheer diversity is a puzzle in itself. Why do these smallest of galaxies refuse to conform to a few neat categories? The answer seems to lie in their delicate and tumultuous lives. A grand spiral galaxy possesses a deep, powerful gravitational well that acts like a cosmic stabilizer, quickly smoothing out any disturbances and enforcing order. Its immense mass dictates a certain structure, but a dwarf galaxy is a far more fragile system, its gravity too weak to easily impose such discipline. This makes it incredibly sensitive, its final shape sculpted by a constant tug of war between internal violence and external forces. Internally, the blast waves from supernova can churn the galaxy's gas, puffing it up or triggering asymmetric bursts of star formation that leave one side brighter and more extended than the other, creating a lopsided, irregular appearance. Externally, the gravitational tides from a nearby giant galaxy can slowly warp a once spherical dwarf, stretching it into a teardrop shape or completely disrupting its structure over billions of years. Even their merger histories play a role. Two small dwarfs colliding will not create a neat, larger elliptical galaxy as massive galaxies do. Instead, they are more likely to merge into a single, messy, and turbulent irregular galaxy, a testament to a violent past that its weak gravity cannot erase. This wild diversity tells us that for a small galaxy, its final form is not preordained. It is a living record of everything that has ever happened to it, a unique product of its personal history of birth, internal rebellion, and cosmic bullying. Their shapes are not just appearances, they are stories. The wild diversity of dwarf galaxy shapes is a testament to their chaotic lives, but one of the most profound puzzles comes from their sheer lack of presence. We face another deep contradiction between our theoretical predictions and the actual sky, a problem so striking it has earned a dramatic name. This is the too big to fail problem. Our most sophisticated computer simulations of cosmic structure do more than just predict thousands of small dark matter halos around the Milky Way. They also predict that the very largest and most massive of these halos should have become the homes for the biggest and brightest dwarf galaxies in our cosmic neighborhood. Think of these halos as the most prime real estate in the early universe, vast gravitational wells with the perfect conditions to pull in enormous amounts of gas and forge countless brilliant stars. According to our models, these halos are simply too substantial, too powerful to have failed at forming prominent galaxies. Yet when we look for these predicted giants, we find only faint, unimpressive dwarfs. The most massive dark matter halos appear to be inhabited by surprisingly small and dim galaxies. It is as if we surveyed a bustling planet and found its most fertile, resource-rich valleys completely empty, while life struggled to survive only on the barren mountaintops. This forces a difficult question upon us. Why did galaxy formation fail in the very places it should have succeeded most spectacularly? The problem points to a potential flaw in our understanding of the fundamental physics at play. One possibility is that our assumptions about dark matter are incorrect. If dark matter is not completely cold and collisionless, but instead has some slight warmth or a tiny ability to interact with itself, it would change how it clumps together. This could make the cores of the largest halos less dense, preventing them from holding onto their gas tightly enough to form a wealth of stars. The galactic engines would simply be too weak to ignite. Another explanation lies in the complex astrophysics of star formation itself. Perhaps these massive halos did pull in vast amounts of gas, but that gas was then violently expelled by an early frenzy of supernova explosions. In a smaller halo, this would be a death sentence, but in a massive one, some gas might have fallen back in to form later generations of stars. If our models are wrong about how gas cools, collapses, and is regulated by feedback, we could be overestimating how bright these satellite galaxies should be. The too big to fail problem is not about missing galaxies, but about galaxies that are far too feeble for their massive foundations. It suggests that something is suppressing star formation in the most promising places, leaving us to wonder if the fault lies in the dark matter scaffolding of the universe or in the turbulent, fiery physics of how stars are born. This chaotic diversity of form is not the only way dwarf galaxies defy our expectations. Far from the gravitational turmoil of galaxy clusters, another class of these tiny systems thrives in the profound emptiness of cosmic voids. These isolated dwarfs are cosmic hermits, adrift in vast regions of space that are largely devoid of other large galaxies. Logic would suggest that in these quiet, undisturbed environments, a dwarf galaxy would be free to follow its natural course, calmly converting its reservoir of primordial gas into new stars over billions of years. Yet when we observe these isolated systems, we find a story that is far more complex and surprising. Many of these void dwarfs are not the vibrant stellar nurseries we might predict. Instead, they often display a puzzling lack of star formation, appearing quiet and uneventful even though they are surrounded by the raw fuel needed to create suns. This suggests that the suppression of star formation is not always a drama orchestrated by external bullies. In the deep quiet of a void, something internal or intrinsic can also shut down the stellar production line. One key factor appears to be the nature of the gas itself. In these primordial voids, the hydrogen gas may be too warm or too diffuse, lacking the dense, cold pockets necessary to collapse under its own gravity and ignite new stars. Without the external pressure from a galaxy cluster or a nearby giant to help compress this gas, the star formation process simply fails to start efficiently. It is like having a pile of dry wood but no kindling or spark to get a fire going. Another possibility is that their own gentle internal dynamics are to blame. In the absence of any external shocks or collisions to stir things up, the gas in these isolated dwarfs may remain too calm and stable, never experiencing the turbulence that typically seeds the birth of new stellar generations. These cosmic hermits challenge the idea that a quiet life is a productive one. Their subdued nature reveals that star formation is a delicate dance, one that can be halted not only by violence from without, but also by a profound stillness from within. The serene existence of a cosmic hermit seems a world away from this new, mind-bending role. It defies all intuition, but these faint, seemingly insignificant dwarf galaxies can act as natural telescopes, warping the fabric of space itself. This phenomenon is gravitational lensing, a dramatic effect predicted by Einstein, where a massive object acts like a lens, bending and magnifying the light from objects far behind it. We typically associate this cosmic trick with colossal galaxy clusters, whose immense gravity can twist background galaxies into spectacular arcs and rings. But for a tiny dwarf galaxy with so few stars, the idea seems almost laughable. Its visible mass is far too small to produce such a dramatic effect. The secret, once again, lies in the invisible. A dwarf galaxy's enormous, concentrated halo of dark matter provides the gravitational muscle. While it cannot create the stunning Einstein rings of a massive cluster, it produces a more subtle yet equally powerful effect known as weak gravitational lensing. Here, the dwarf's gravity does not dramatically distort a single background galaxy. Instead, it minutely warps the shapes of thousands of faint galaxies in the distant background. Individually, each galaxy's distortion is tiny, almost imperceptible. but by studying the collective statistical alignment of thousands of these subtly stretched galaxies, astronomers can map the invisible gravitational field of the foreground dwarf. It is like looking at a distant street lamp through the heat waves rising from a quiet, narrow road. You do not see a perfect, magnified image of the lamp. Instead, its light shimmers and wavers in a specific pattern, a pattern that tells you everything about the invisible heat distorting the air. This weak lensing technique provides a completely independent way to weigh these enigmatic systems. When astronomers apply this method, the results are unequivocal. They confirm the staggering mass of these dwarfs, a mass that is almost entirely dark. This independent verification silences any lingering doubts. The frantic orbits of stars inside the galaxy and the subtle warping of space around it both point to the same astonishing conclusion. These are not just collections of stars, they are dense, massive nuggets of dark matter with a sprinkling of stellar light on top. This powerful tool allows us to see the invisible architecture of the cosmos directly, using the distorted light of the distant universe to weigh the ghosts in our own galactic backyard. The same dark matter that warps space also seems to preside over a strange kind of cosmic chemistry. Deep within these tiny galaxies, astronomers have uncovered bizarre and varied chemical compositions that defy the norms of our own galactic neighborhood. The stars in many dwarf galaxies show unusual abundance patterns of elements like carbon, nitrogen, and oxygen, ratios that are strikingly different from what we find in the vast majority of stars in the Milky Way. This is not a minor discrepancy. It suggests that the very recipe for building stars and planets can vary dramatically from one galaxy to another. In our own galaxy, chemical enrichment was a long, messy, and well-mixed process, with countless generations of stars contributing their elemental ashes to the galactic pot. But in a small, fragile dwarf galaxy, the process was far more isolated and subject to chance. The chemical fingerprint of a dwarf galaxy can be dominated by just a few rare cataclysmic events. One possibility is that a specific type of supernova, one that is now rare in the Milky Way, was far more common in the early universe. For instance, pair instability supernova, which come from the deaths of the very first monstrously massive stars, would have scattered a unique blend of elements into the surrounding gas, a signature that would be preserved in the next generation of stars. Alternatively, the slow, steady winds from asymptotic giant branch stars, which are aging suns in their final, bloated phase, could have been the primary chemical contributors. These stellar winds are rich in specific elements like carbon, and if a dwarf galaxy experienced a single, intense wave of these stars, their collective output could have imprinted a unique chemical signature on the entire system, one that was never overwritten by later events. This makes each dwarf galaxy a unique natural experiment in nucleosynthesis, the cosmic process of element creation. They are not just collections of stars, but sealed time capsules preserving the isolated chemical history of a small pocket of the early universe. By reading these strange stellar chemistries, we are learning that the elements we take for granted, the very stuff of our world and our bodies, could have been blended together in profoundly different ways elsewhere in the cosmos. The bizarre chemistry within dwarf galaxies is only the beginning of their defiance. A far more profound structural enigma orbits our own galactic home. Around the Milky Way, our satellite dwarf galaxies are not scattered randomly like a swarm of bees. Instead, they are aligned with an eerie precision, tracing out a vast, thin, and rotating disk. Astronomers call this the vast polar structure, a great plane of satellites that cuts across our galaxy. This is not what our standard cosmic models predict. According to the lambda-cold dark matter model, dwarf galaxies should fall into the Milky Way's grasp from all directions, their orbits chaotic and isotropic, creating a spherical cloud around us. The existence of this vast structured plane is a direct contradiction. It is as if you dropped a handful of marbles and they all landed neatly in a perfect spinning circle. How could such a coherent structure emerge from a process that should be fundamentally random? This is not a minor oddity. It strikes at the heart of how we believe galaxies assemble over time. One compelling explanation is that this plane is a fossil from a single, ancient event. Perhaps these dwarf galaxies did not arrive one by one, but were all part of a larger group, a kind of galactic family that was accreted together in the distant past. Their shared motion could be an echo of that common origin, a coordinated flight that has persisted for billions of years. This would be a dramatic story of our galaxy's violent youth. Yet, an even more radical possibility exists. The persistence of this thin, rotating plane might be telling us that our understanding of gravity and dark matter is incomplete. Perhaps dark matter, the invisible scaffolding of the cosmos, has properties we have not yet accounted for, properties that allow for such vast, coherent structures to form and endure. The plane of satellites is more than just a curious alignment. It is a silent challenge written in the orbits of our smallest neighbors, forcing us to question whether the universe is as chaotic as we believe. The silent challenge of our galactic plane is echoed by a roar from the most unexpected of places. Deep within the tranquil hearts of some dwarf galaxies, astronomers have found monsters. Supermassive black holes, behemoths with the mass of millions of suns, are lurking in these smallest of cosmic islands. This discovery shatters a long-held assumption. We thought these gravitational giants were the exclusive property of large galaxies, that a galaxy's central black hole scaled with its size. Our own Milky Way's central black hole, Sagittarius A star, is a fitting 4 million solar mass resident for a grand spiral. But finding a black hole of similar or even greater mass inside a dwarf galaxy 100 times smaller is like finding a skyscraper's foundation under a suburban cottage. It defies all expectations of cosmic proportion. One of the most telling examples is the dwarf starburst galaxy Hennies 210. This small, turbulent galaxy is a frenzy of new star birth, and at its core lies a supermassive black hole. But here is the real twist. Instead of acting as a destructive force, this black hole appears to be a creative one. Observations show a vast, hot outflow of gas streaming from the core, and where this jet slams into a dense molecular cloud, it is triggering a fireworks display of new star formation. It is a cosmic paradox, a black hole, an object known for its relentless pull, actually giving birth to new suns. This turns the traditional narrative on its head. We often think of black holes as engines of destruction, but in the compact, intimate environment of a dwarf galaxy, their influence can be more nuanced, their powerful outflows compressing gas and seeding new stellar nurseries. The existence of these dwarf giants forces a profound rethinking of black hole origins. How did these monsters get there? They are likely ancient relics, the original seed black holes from the dawn of time. In the early universe, the first stars were immense and lived short, violent lives, collapsing directly into black holes of perhaps a few dozen solar masses. The discovery of supermassive black holes in today's dwarfs suggests that some of these seeds found their way into small galaxies and simply stopped growing. Perhaps their host galaxy was stripped of gas early on, or maybe it never merged with another, cutting off the fuel supply needed for the black hole to feast and expand. These dwarf galaxies, then, are not just cosmic backwaters. They are living fossils, preserving the conditions of the early universe and holding the original seeds that, in other places, grew into the unimaginably large black holes that now rule the centers of every major galaxy. They offer us a unique window into the very first steps of how these cosmic titans were born. These ferocious blue nuggets are the wild, untamed ancestors of the dwarfs we see today. In the early universe, astronomers have spotted these incredibly compact, blazingly blue galaxies, small in size but furiously giving birth to stars. They are the opposite of the feeble, ancient dwarfs we find nearby. A blue nugget galaxy crams a staggering number of new, hot, massive stars into a tiny volume, shining with an intense blue light that marks it as a cosmic powerhouse. The sheer density of this activity is what makes them so puzzling. They are forming stars at a rate that could populate an entire galaxy in a relatively short cosmic time, yet they do not grow into majestic spirals like the Milky Way. They remain stubbornly small and dense, defying the expectation that such prolific star formation should lead to major growth. The central question is what stops them. How does such a ferocious firestorm of creation simply burn out, leaving behind the quiet, red, and dead dwarf spheroidals we find in our modern universe? The answer seems to lie in a self-destructive cycle of feedback. Inside a blue nugget, the sheer intensity of star formation becomes its own undoing. All those massive, brilliant stars live fast and die young, exploding as supernova in a relentless, coordinated fury. These explosions blast the galaxy's remaining gas reservoir out into the void. It is a case of cosmic arson, where the fire gets so hot and violent that it burns up all its own fuel in a single, glorious, and ultimately terminal burst. This violent expulsion of gas quenches the galaxy in an instant. Without the raw material to make new stars, the blue nugget's brilliant light fades. Its massive blue stars quickly die off, leaving behind only the longer-lived, older, and redder smaller stars. The galaxy transforms from a blazing blue nugget into a quiet red nugget, and eventually, over billions of years, into the faint dwarf spheroidal we recognize today. This dramatic life cycle reveals a universal truth. The destiny of a galaxy is not just about how many stars it can create, but about whether it can hold onto the fuel to keep creating them. For these small, intense galaxies, their greatest burst of life was also their death sentence. Some dwarf galaxies have taken their defiance of cosmic convention to an even more spectacular extreme. They have adorned themselves with vast, luminous rings that spin on a completely different axis from the rest of the galaxy. Picture a dinner plate spinning on its edge, and then imagine a glowing hula hoop rotating around the plate's rim, perpendicular to its surface. This is the bizarre architecture of a polar ring galaxy, and one of the most stunning examples is NGC 4650A. At its core lies a fairly typical, ancient dwarf spheroidal galaxy, a collection of old red stars. But encircling this core, tilted by a full 90 degrees, is a brilliant ring of young blue stars, gas and dust, a separate structure with its own distinct orbit. How could such a beautifully unnatural configuration possibly come to exist? The leading theory points to a dramatic act of cosmic theft, a galactic collision that unfolded over billions of years. In one scenario, a smaller dwarf galaxy ventured too close to a larger one. The gravitational tides of the larger galaxy could have slowly torn the smaller one apart, stripping away its gas and stars and stretching them into a vast, rotating ring that settled into this perpendicular orbit. In another, the central galaxy might have cannibalized a vast stream of intergalactic gas, a cosmic filament flowing through the void. As this gas was captured, it would have naturally settled into a stable orbit that was perpendicular to the galaxy's main plane, eventually collapsing to form new stars and creating the brilliant ring we see today. For astronomers, these celestial oddities are more than just beautiful accidents. They are unparalleled natural laboratories for weighing the invisible. The central galaxy and its perpendicular ring are essentially two independent systems, one nested within the other, both moving under the influence of the same invisible dark matter halo. By measuring the rotation speed of the stars within the central spheroid, and then comparing it to the speed of the gas and stars in the outer ring, scientists can perform a direct, three-dimensional mapping of the galaxy's gravitational field. It is like having two separate speedometers installed in different parts of a car, allowing a mechanic to diagnose the unseen engine. The ring acts as a probe, tracing the shape and distribution of the dark matter that holds the entire bizarre structure together. These polar rings offer some of the most compelling and direct evidence for the existence of dark matter, revealing its hidden grip on the cosmos through the graceful, tilted dance of stars and gas. This strange celestial architecture brings us to a subtle but critical discovery hidden in the starlight itself. Within the faintest dwarf galaxies, astronomers have found an unexpected population boom, not of stars but of stellar partnerships. These ultra-faint dwarfs are teeming with binary star systems, pairs of stars locked in a mutual gravitational dance. The detection of these cosmic couples relies on a delicate technique. By repeatedly measuring the spectrum of a star's light, scientists can watch for a subtle back and forth wobble in its color. If a star is moving toward us, its light is shifted slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. A regular, rhythmic oscillation between red and blue shift is the telltale signature of an invisible companion, a binary partner tugging the star into a cyclical orbit. In many of these quiet dwarfs, this wobble is surprisingly common. But why does this abundance of stellar pairs matter so profoundly? The implications ripple through our most fundamental cosmic measurements. The primary method for weighing a galaxy involves observing how fast its stars are moving. Those high velocities are what reveal the presence of dark matter's immense gravitational pull. But here is the catch. A star that is part of a binary system will appear to be moving rapidly as it orbits its partner, even if the binary pair as a whole is moving slowly through the galaxy. If astronomers mistake these intimate orbital dances for the random, high-speed motions of single stars, they would drastically overestimate the galaxy's total mass. It creates a phantom gravity signal, a cosmic illusion where stellar partnerships can mimic the effects of dark matter. This means the incredible dark matter dominance we measure in some dwarfs could be, at least in part, a mirage caused by a sky full of binary stars. Untangling this knot is essential for getting a true census of dark matter. Beyond this gravitational masquerade, the sheer number of binaries is a clue to a different mystery. It points to the unique conditions of the early universe. Star formation in those primordial, gas-rich dwarfs may have naturally favored the creation of binary systems. Dense, collapsing clouds of pristine gas could have fragmented more easily into multiple stellar seeds instead of single, isolated suns. The overabundance of binaries in these cosmic fossils suggests that the first galaxies were not just collections of stars, but vast networks of stellar families, a fundamental truth about cosmic beginnings that is preserved only in these faintest of lights. This quiet abundance of stellar partnerships stands in stark contrast to the violent, elemental forges these galaxies once hosted. The greatest irony of the cosmos may be this, that the smallest, most unassuming galaxies were the primary creators of the heaviest elements in the universe. Every atom of gold in a piece of jewelry, every particle of iron in your blood, was forged in the heart of a dying star, but not just any star and not just anywhere. The very first generations of stars were colossal behemoths, hundreds of times more massive than our sun, and they lived fast and died violently. Where did these stellar giants predominantly live? In the dense, gas-rich environments of the early dwarf galaxies, these tiny systems were the universe's first and most prolific heavy element factories. A single massive star would blaze through its nuclear fuel in just a few million years, a cosmic blink of an eye, before exploding in a supernova of unimaginable power. In that final, catastrophic detonation, the intense heat and pressure fused lighter elements into heavier ones, scattering newly forged atoms of carbon, oxygen, iron, and even gold across the surrounding space. Because dwarf galaxies were so small and had such weak gravity, they could not hold onto this enriched material. The very supernova that created these precious elements would also blast them out into the intergalactic void. This was a chaotic, messy process, but a profoundly important one. These elemental winds flowing from countless dwarf galaxies slowly polluted the pristine hydrogen and helium of the early cosmos, seeding vast clouds of gas with the ingredients for rocky planets and eventually life. Think of a dandelion releasing its seeds to the wind. Each dwarf galaxy was like that, scattering the seeds of future complexity far and wide. The gas that would later collapse to form our own Milky Way and our own solar system was already enriched by these ancient, diminutive cosmic forges. So the iron in Earth's core and the gold in its crust were likely forged billions of years before our galaxy even existed, inside stars that lived and died in galaxies so faint we can barely detect their descendants today. We are quite literally made from the ashes of stars that once shone in the universe's smallest islands. The profound stillness of cosmic voids is not always a guarantee of continued life. Astronomers have made a startling discovery in these quiet, low-density regions of space, far from the violent crowds of galaxy clusters. Here, they have found quenched dwarf galaxies, systems where star formation has been completely shut down. This is deeply counterintuitive. In the isolation of what is called the field, a galaxy should be free from the external pressures that typically strangle star birth. It should have a vast, private reservoir of primordial gas to draw upon, leading to a long and productive life of creating new suns. Finding a galaxy in this environment that has simply given up is like finding a fertile, well-watered field that has lain completely fallow for eons. The very silence of the location becomes the mystery. So what force could have quenched these isolated systems? The prime suspect is a process of internal self-destruction. In a dwarf galaxy's early, vigorous years, it may have experienced a ferocious burst of star formation. The resulting supernova would have exploded in a coordinated fury, and in a small galaxy with weak gravity, these blasts can easily overwhelm the system. They can drive a powerful galactic wind, ejecting the entire remaining gas supply out into intergalactic space. The galaxy, having burned through its fuel in a single glorious burst, is left permanently quenched, a ghost of its former self adrift in the cosmic emptiness. But there is another, more subtle cosmic force that could be at work, a relic from the universe's youth. This is the ultraviolet background radiation, a pervasive glow left over from the epoch of reionization. This universal energy field acts like a constant, gentle heat, warming the hydrogen gas that a galaxy needs to form stars. For a large galaxy with strong gravity, this background heat is a minor nuisance. But for a small dwarf, it can be a death sentence. The galaxy's weak pull cannot overcome this external heating to compress the gas into the cold, dense clouds required for star birth. The gas remains warm and diffuse, forever unable to collapse, so a quenched dwarf in the field presents us with two haunting possibilities. Did it die by its own hand in a dramatic internal suicide, or was it slowly stifled by the faint, lingering warmth of the universe itself, a victim of a cosmic climate it could never escape? This ghostly presence is far more vast than we ever suspected. The dark matter halo enveloping a dwarf galaxy is not a tight, dense shroud clinging to its stars. Instead, it is an immense, wispy cloud that stretches for hundreds of thousands of light years, a tenuous ghost far larger than the tiny collection of stars it hosts. We have mapped these colossal, invisible structures through a combination of powerful computer simulations and the subtle art of gravitational lensing. The results reveal a structure that is profoundly fluffy, its density gently increasing toward the edges rather than spiking sharply at the center. This gentle profile is the heart of a deep cosmological mystery known as the core cusp problem. Our foundational model of the universe, lambda cold dark matter, makes a very specific prediction. It says that dark matter, being cold and collisionless, should pile up in a steep, dense peak or cusp at the very center of these halos. Think of a pile of sand with its highest, most concentrated point right in the middle, but the observations tell a completely different story. The dark matter in dwarf galaxies appears to have a soft, uniform core, like a cloud of diffuse smoke with no dense center at all. This is not a minor discrepancy. It is a direct conflict between our most successful model of the cosmos and the actual, observed architecture of these dark matter-dominated systems. So what is smoothing out these central cusps? One compelling idea is that dark matter is not completely cold and non-interacting. Perhaps dark matter particles can actually collide with one another, a theory known as self-interacting dark matter. In this scenario, as these particles move within the halo, their tiny interactions generate a kind of friction or pressure. Over time, this would naturally redistribute the dark matter, pushing it away from the center and creating the soft, fluffy cores we detect. It is like shaking a bag of marbles. They will naturally settle into a more even, less peaked distribution. Another radical possibility is that dark matter is not cold at all, but is instead warm. Warm dark matter would be made of faster-moving, lighter particles. This inherent speed would prevent it from clumping together too tightly on small scales, naturally explaining the lack of a dense central cusp in dwarf galaxies. The core cusp problem is more than just a technical puzzle. It is a direct observational clue, a fingerprint left at the scene of a cosmic crime that is forcing us to reconsider the fundamental nature of the universe's most abundant substance. The very fluffiness of these ghostly halos might be the key that unlocks the true identity of dark matter itself. This cosmic defiance of expectation has a beautiful and violent origin. While most dwarf galaxies are ancient relics, a special class is born from pure chaos in the present-day universe. These are the tidal dwarf galaxies, and they emerge not from the primordial dark matter of the cosmos, but from the wreckage of colossal collisions. When two massive spiral galaxies slam into each other, they do not simply merge quietly. Their gravitational embrace rips vast streams of gas and stars from their spiral arms, hurling this material out into the void. Within these ejected rivers of debris, something miraculous happens. The gas becomes turbulent and collapses under its own gravity, igniting a firestorm of new star formation. These newborn stellar systems condensing from the carnage are the tidal dwarf galaxies. They are cosmic phoenixes rising from the ashes of galactic destruction. Their composition is what makes them truly revolutionary. A tidal dwarf galaxy is built almost entirely from the normal, baryonic matter that was torn from its parent galaxies, the same kind of matter that makes up our planets, our sun, and us. It should contain very little, if any, dark matter. Why? Because in a galactic collision, the dark matter halos of the two large galaxies, being vast and diffuse, simply pass through one another. They do not collide or get pulled out into the tidal tails in the same way that the concentrated gas and stars do. The dark matter remains as a background ghost, while the normal matter is ripped out to form these new, bright objects. This gives astronomers a powerful and rare laboratory. By studying the dynamics of a tidal dwarf galaxy, they can observe a system where gravity is dominated by the stuff we can see. They can measure how stars move within these galaxies without the overwhelming gravitational influence of dark matter clouding the picture. This provides a crucial test for our theories. Do these dark matter-free galaxies behave exactly as Einstein's laws of gravity predict they should when only normal matter is present? Or do we still see anomalies that might point to something else at work? Tidal dwarf galaxies offer a clean separation, a chance to watch the universe's two primary ingredients, the light and the dark, acting independently. They are a direct, natural experiment created by the most violent events in the cosmos, allowing us to witness the pure dance of ordinary matter, free from the shadow of the invisible. The quiet, steady pulse of stars within dwarf galaxies is now echoing through the highest levels of cosmology, amplifying one of science's greatest modern mysteries. This is the Hubble constant tension, a stubborn discrepancy in the measured expansion rate of the universe that refuses to go away. At its heart, the problem is about distance. To measure how fast the cosmos is growing, we need to know how far away things are with incredible precision. This is where dwarf galaxies and the special stars they contain become indispensable cosmic mile markers. Inside these small galaxies, astronomers find pulsating variable stars called Cepheids and Aurora Lyrae. These are not just any stars, they are standard candles, celestial lighthouses with a known intrinsic brightness. A Cepheid star beats with a regular rhythm, and the period of its pulse is directly tied to its true luminosity. By measuring how bright it appears from Earth and comparing that to its known true brightness, astronomers can calculate its distance with remarkable accuracy. It is like knowing the exact wattage of a light bulb. By seeing how dim it looks from far away, you can work out precisely how far you are standing from it. Aurora Lyrae stars serve a similar role, providing a reliable distance measurement for older stellar populations. For decades, these stars in nearby dwarf galaxies have been the foundation of the cosmic distance ladder, the step-by-step method used to measure the universe's local expansion rate. Yet this locally measured value, painstakingly pieced together from the light of Cepheids in dwarfs and other galaxies, consistently disagrees with the value predicted from the afterglow of the Big Bang, the cosmic microwave background. The early universe measurement and the modern universe measurement do not match. One suggests a faster expansion, the other a slower one. This is not a small error margin. It is a significant and persistent gap that has survived years of improved observations and data analysis. The latest and most precise data from these dwarf galaxy standard candles have only deepened the conflict, confirming that the discrepancy is real. This tension is now so severe that it points to a potential crisis in our standard model of cosmology. Perhaps dark energy, the force driving the acceleration, is not constant but is changing over time. Maybe there exists a new, unknown type of neutrino or another exotic particle that altered the early universe's energy balance. Or, in the most thrilling possibility, our understanding of gravity itself may need a fundamental revision. The humble dwarf galaxy, with its pulsating stellar beacons, has placed us at a crossroads. Its faint light is forcing us to confront the possibility that we are on the verge of a revolution in physics, one that could rewrite our story of the cosmos from its very beginning. The cosmic confusion only deepens with a class of objects that defies simple classification. These are the ultra-compact dwarfs, cosmic anomalies that are neither true star clusters nor proper galaxies, but something unsettlingly in between. Imagine a sphere of stars so densely packed that millions of suns are crammed into a space just a few hundred light-years across, a volume that would fit comfortably within the gap between our Sun and its nearest stellar neighbors. An ultra-compact dwarf possesses the mass of a small dwarf galaxy, often tens of millions of times the mass of our own Sun, yet it is 100 times smaller than a typical dwarf spheroidal. This gives it a staggering density, a brilliant, overstuffed nugget of starlight that outshines any known globular cluster. Their very existence blurs a line we once thought was clear. So what are they? The debate over their origin is a cosmic identity crisis. One compelling theory paints a violent picture. An ultra-compact dwarf may be the surviving heart of a much larger dwarf galaxy that ventured too close to a galactic giant. As the larger galaxy's gravitational tides ripped away the dwarf's outer layers of stars, all that remained was its dense central nucleus, a bare core left to wander space. This would make every ultra-compact dwarf a ghost, the lone surviving organ of a dismembered celestial body. The alternative is that they are simply the most massive globular clusters ever to form, born in a single, intense burst of star formation within the early universe. The evidence for their strange nature goes beyond mere size. When astronomers weigh these objects by measuring the velocities of their stars, they find something startling. Many ultra-compact dwarfs are far too heavy for their starlight. Their stars whip around at speeds that suggest the presence of a tremendous, unseen mass anchoring the center, a mass that cannot be accounted for by the stars alone. This points to the same shocking discovery we found in larger dwarfs, the potential presence of a central supermassive black hole. Finding such a gravitational monster at the heart of what looks like a simple star cluster is profoundly disorienting. It further erodes the boundary between a cluster, which is a gravitational structure, and a galaxy, which is defined by the gravitational dominance of dark matter. An ultra-compact dwarf with a central black hole is no longer just a collection of stars. It is a system with a dynamic, complex heart, a miniature galaxy in its own right. These objects force us to admit that our categories are human inventions. The universe does not care for our neat labels, creating instead a continuous spectrum of celestial structures, from the simplest star cluster to the most complex galaxy, with the enigmatic ultra-compact dwarf sitting squarely in the middle, challenging everything we thought we knew. These final cosmic rebels refuse to be neatly labeled. Some dwarf galaxies exhibit a true split personality, blurring the line between two distinct galactic classes in a single, chaotic system. Take the intriguing case of NGC 55. This nearby dwarf displays a flattened, rotating disk of gas and young blue stars, a hallmark of spiral structure. Yet it also possesses a prominent, more diffuse spheroidal component of older, redder stars, a classic feature of elliptical galaxies. It is as if two completely different galaxies are inhabiting the same space, one vibrant and dynamic, the other quiet and ancient. This hybrid nature directly challenges the century-old Hubble tuning fork diagram, the iconic system that neatly divided galaxies into orderly spirals and smooth ellipticals. Dwarfs like NGC 55 expose that classification as an oversimplification. Their split personalities suggest a far more fluid and continuous evolutionary pathway. A dwarf galaxy's final form is not a fixed identity, but a transient state highly sensitive to its personal history. A quiet, spheroidal dwarf might have its gas compressed by a close encounter with a neighbor, triggering a burst of star formation that organizes into a temporary disk. Conversely, a dwarf spiral could have its delicate disk shredded and puffed up by gravitational tides over billions of years, leaving it a messy hybrid. Their appearance becomes a snapshot in time, a reflection of their most recent interaction or internal upheaval. This final discovery brings our journey full circle, revealing that the greatest secret of these tiny galaxies is their profound refusal to be simple. They are not just building blocks or fossils or dark matter labs. They are dynamic, ever-changing entities whose chaotic beauty reminds us that the universe resists our every attempt to put it into a tidy box. Their small size is the universe's greatest deception. These 25 discoveries reveal that dwarf galaxies are not mere footnotes in the cosmos, but central characters in its grandest story. They have challenged our deepest convictions, forcing us to rewrite the rules of dark matter, galaxy formation, and cosmic evolution. From the ghostly halos that warp space itself to the ancient starlight that ended the cosmic dark ages, these tiny titans have proven that significance is not a matter of scale. They hold the fossilized seeds of supermassive black holes, the scattered ashes of the first heavy elements, and the subtle clues to the universe's accelerating expansion. Every paradox, from the missing satellites to the too big to fail problem, has not been a setback but a guidepost pointing toward a richer, more complex reality than we ever imagined. So the next time you gaze up at the night sky, remember that the true drama is not only in the brilliant sweep of the Milky Way. It is also in the faint, silent glimmers orbiting at the edge of vision, each one a universe of mystery waiting to be understood. We would love to hear which of these strange discoveries captivated you the most. Share your thoughts and questions in the comments below, and let us continue this cosmic conversation together. This great cosmic mystery is far from over, its next chapter already being written by the most ambitious telescopes ever conceived. Our journey into the faintest corners of the cosmos is accelerating, powered by a new generation of observatories designed to pry open the secrets dwarf galaxies have guarded for so long. The James Webb Space Telescope, with its infrared eyes, is peering back to the cosmic dawn, searching for the very first dwarf galaxies as they ignite. It seeks to witness these primordial systems in their infancy, to see if they truly were the blue, star-forming nuggets we suspect, and to understand how their collective light first pierced the cosmic fog. Meanwhile, here on Earth, the Vera C. Rubin Observatory will soon begin a decade-long cinematic survey of the entire southern sky. Its power lies in volume and repetition, scanning the heavens night after night. This will allow it to discover thousands of new ultra-faint dwarf galaxies orbiting our own Milky Way and nearby galaxies, finally giving us a complete census of our local galactic neighborhood. It will find ghosts we never knew existed, potentially solving the missing satellite problem by revealing a hidden population so dim they have until now been invisible. And then comes the Nancy Grace Roman Space Telescope, a wide-field powerhouse that will combine the deep vision of James Webb with the vast sky coverage of Rubin. Roman is poised to perform a celestial census of staggering scale, mapping the distribution of dark matter itself through the subtle warping of light from billions of distant galaxies. By observing how dwarf galaxies are embedded within their vast, fluffy dark matter halos, it could deliver the most precise measurements yet of the properties of this mysterious substance. Will it finally confirm if dark matter is warm or self-interacting, solving the core cusp problem that has puzzled us for decades? These telescopes are not just bigger, they are smarter, working in concert to attack the mystery from every angle. They will not merely take pictures, they will collect stories, tracing the complete life cycle of these tiny titans from their violent births to their quiet old age. We stand on the precipice of a new era of discovery, where the faintest glimmers in the sky will no longer be unanswered questions, but the very keys to unlocking the fundamental laws of the cosmos. The greatest revelations are still waiting, hidden in the dark, soon to be brought to light.